Hello everyone. We are now going to begin our lecture on the third section of chapter 4 on number systems. So in this section we are going to talk about representing numbers in different bases. So far we have only learned about the Hindu-Arabic system, the base system of 10, the decimal system, and that had base 10, which we are all familiar with. And we learned about a couple of ancient systems, particularly the Babylonian system. It used base 60, and the Mayan system used slightly different. It was based of base 20, but then they also multiplied that by 18 for some of its places, right? Now we will talk about other bases, which could be base 2, base 8, base 16. Now, base 2, base 8, and base 16 are used extensively in the world of computer science. But we can represent numbers with any base 3, base 4, base 5, base 6, any base. So we are going to learn about how we do that and how to convert from the base system from other bases to the decimal base system, and also later on in subsequent sections we are going to learn how to perform operations like addition, subtractions, multiplications, and divisions with numbers represented in different bases. So we are going to learn the following in this section. First of all, to convert between Hindu-Arabic numerals and numerals with bases less than 10. And we'll focus on basically bases 2, 3, 4, 5, 6, 7, 8, essentially. All right. I don't think we will talk much about base 9. But all bases, we couldn't represent all bases with less than 10. All right. And then we will also talk about bases greater than 10. And for that, we will deal with bases 12 and 16. All right. So we'll also learn to convert between Hindu-Arabic numerals and numerals with bases greater than 10. So to review the concept behind positional values, we already learned that the Hindu-Arabic system is based on the base 10 system, where the first or the units place has a positional value of 1, and that comes from the base 10 to the power 0, right? 10 to the power 0 is 1. And then the next place to its left is 10 to the power 1, which is just 10, and then it proceeds that way as we move from the right to the left. So 10 squared for the third place value, 10 to cube, 10 fourth, and so on. Right? Then we also learned about the Babylonian system, which had base 60, and it worked the same way as well. The first position on the extreme right was a 1, and that is the equivalent of 60 raised to the power 0. Then we had 60 to the power 1, 60 squared, 60 cubed, and 64. Now the same concept is going to be extended to other bases as well. So when we talk about base 2 or base 3 or base 4 or any other base, it's going to follow the same thing, except instead of 10 to the power 0, the extreme digit is going to be, if we are talking about base 2, it's going to be 2 to the power 0, 2 to the power 1, 2 to the power 2. So that's how the place values are going to be. So we are going to use the same logic, apply the same logic for other bases. So if you have understood the positional values concept, then it should be easy for you to represent numbers in different bases. Now, The positional values and bases say that 10 and 60 are called the bases of the Hindu-Arabic and Babylonian systems respectively. This is what we just said in the previous slide. And then any counting number greater than 1 may be used as a base. It has to be greater than 1 though. If a positional value system has base b, then its positional values will be b to the fourth, b to the b cubed, b squared, b, and then 1. All right. So in other words, and actually we should always move from the right to the left, from the lowest digit to the highest digit. So the place values are going to be b to the power 0, b to the power 1, b to the power 2, b to the power 3, b to the power 4, and the exponents increase as we move to the left. All right, that's all this slide is trying to explain. So b can take any number greater than 1. All right. Now the positional values in a base 8 system are 1 followed by 8 to its left, followed by 8 squared, followed by 8 cubed, followed by 8 to the power 4, and that in the base 2 system would be 1 followed by 2 to the power 1, 2 squared, 2 cubed, 2 to the power 4, and so on. Now we are going to start learning about the other base numeration systems with the binary or the base 2 system. Now the base 2 system is used widely in computer applications and for electronic communications as well. Now for the base 2 or any base system, if you remember, we had talked about this earlier, we have numerals which represent 0. All right, we must have numerals to represent any base systems. We must have numerals to represent a 0 and the numbers 1 less than whatever the base value is. So if it's base 2, then we must have a numeral to represent the number that comes before 2. 1 less than 2. So it would be 0 and 1. And these two are the numerals in the binary system. And using these two numerals, 0 and 1, we will create patterns that will not only represent the numbers, but even the letters of the alphabets, the words, and so on, and even images in sophisticated computer systems. Images are represented in the binary. All right, so we will learn how to understand the different patterns in a binary system and how to convert from the base 10 system to the binary system and from the binary system to the base 10 system. All right, so let's look at some of the other information in this slide. The binary base 2 uses only the digits 0 and 1. They can be represented with electronic switches that are either off or on, because computer systems are based on circuits, all right, and these circuits can be turned off or turned on, and it's usually that on-off combination that will lead to representing the information, the data in the computer. And all computer data can be converted into a series of single binary digits. So when we type an A on our keyboard, what the computer does is it picks it up, and at the back, all right, its circuit will convert it to binary digits, all right, and then store it at some place, and then there is a whole process of displaying that on your monitor. All right, so what happens is that even though you have typed A, the computer, right? The computer system doesn't understand the letter A. We have to convert the letter A to a binary code which the computer can understand, and then again when it's time to display it back, then it'll convert the binary that has been stored, the binary combination, the pattern for A that has been stored in the computer, and back to the letter A and display it. All right, so that's how the system works. So each binary digit is known as a bit, which means that this 0 is a bit, this 1 is a bit. We call them bit, and a combination of 8 of these bits represent a byte. All right, so we will learn about that. That will be the base 8 or the octal system. Now, the octal or the base 8 system is a group of 8 bits of data, and 8 bits of data combine to form what is called a byte. So a byte is nothing but a combination of 8 bits. And that's why we use the word octal to represent base 8. The American Standard Code for Information Interchange, also known as ASCII code, determines which pattern is going to be mapped to which letter. For instance, in this case, the byte 0100000001 represents the uppercase A, whereas the byte 01100001 represents the lowercase a. Other characters representations can be found at this website. All right, you don't need to look it up if you don't, unless you are interested in, but it'll give all the patterns. This website will give all the patterns that represent the different letters of the alphabet system, right? Uh, so that's the octal base 8 system, an introduction to it. Now the hexadecimal or the base 8 system, all right, it's the base 8 system, also called the hexadecimal, is used to create computer languages, programming languages, especially the web page languages like HTML, which is the hypertext markup language, the CSS, which is the cascading style sheets, and both are used heavily in creating internet web pages. And computers usually convert easily between binary base 2, octal base 8, and hexadecimal base 16 numbers. So these three systems are used extensively in the world of computers. All right, you will see that the colors, all right, the colors on a computer are represented in hexadecimal, the hexadecimal codes, right? Whereas letters in base 8 octal, and of course binary is the basis of the or is the unit of each of these octal codes that we have. Now, this slide is going to talk about the numerals associated with each base. It says here a place value system with base B has B distinct objects or B distinct symbols to represent 0, so 1 for 0 and 1 for each numeral less than the base. We talked about this previously. So if it is an octal system, then the octal system has base 8, right? So if it is base 8, then the numerals we need to represent base 8 or work with base 8 systems is 1 for 0, 1 for 0, and then a numeral for each value which 1 less than 8. So 1, we need 2, 3, 4, 5, 6, 7, and we stop there. All right, we don't need a numeral for 8. So it has to be 1 for 0 and 1 for each numeral less than the base. So 1, 2, 3, 4, 5, 6, 7. And 7 is 1 less than 8. So we stop there. All right. And then base 6 system, for instance, would have a 0 to represent 0, and then for each numeral less than the base 6, that means we go up to 5. All numerals in base 6 are constructed from these 6 symbols. Likewise, for base 8 system, we start with 0 and then go all the way to 7, like we showed here. All numerals in base 8 are constructed from these 8 symbols. All right? Now, when we are working with numbers of different bases, then we have to indicate somehow what base is associated with a particular number. So it says here a numeral in a base other than base 10 will be indicated by a subscript to the right of the numeral. So if we have the number 1, 3, 4, all right, if it is base 10, and if we are just working with base 10, the decimal system, like we normally do, then you don't need to put a base. But if you're working with different bases at once, then you have to indicate which base the numbers are associated with. So if this is a decimal base, then you have to write the 10 as a subscript towards the right end foot of the last digit. So 1, 3, 4, and then base 10. However, if it's 1, 3, 4, if it's base 5, you have to write the 5 as a subscript next to the 4. The subscript to the 4. All right. So a numeral in a base other than base 10 will be indicated by a subscript to the right of the last numeral. All right. So let's see what they have here. It says 1, 2, 3, and then with a subscript of 5 represents a base 5 numeral. Likewise, 1, 2, 3, base 6 represents a base 6 numeral. The value of 1, 2, 3 base 5 is not the same as the value of 1, 2, 3 sub 10, right? And that is the reason we have to show the subscripts when we are working with multiple bases, because they don't represent the same value. And finally, base 10 numerals can be written without a subscript when we are just working with base 10. All right, but it's good practice to write the 10 when we, especially for this course, because we are learning with working with multiple bases in this chapter especially. First, we will be looking into the bases that are less than 10. Now, the symbols that represent the base itself in any base are 10 sub b. So if we have a number which is 10 base 6, this will evaluate to a 6. If we have 10 base 4, all right, it will always evaluate to a 4. All right, so that's what this is saying. The symbols that represent the base itself are 1 and 0 for any base. All right, and we will now understand why that is so. All right, so here it says 10 sub 5, 10 base 5 represents 5. How? Let's look at the next line here. It says 10 sub 5 is equal to 1 times 5, right, plus 0 times 1, correct? So we multiply by the positional value, each digit by its positional value. So if it's a base 5, let's look at the positional value. The rightmost digit will have positional value of 5 to the power 0, which is a 1. Then the next one will have a positional value 5 to the power 1. All right, so what this means is that if we have 10 sub 5, as in this case, as they've shown here, then the uh, the 0 is multiplied by 1 for a 0, and then you add 1 times 5 and you will get 5 plus 0, which is a 5. All right, so, and you can try this with any other base and you will always get a numerical value which will be equal to whatever base you worked with. Okay, now let's see what they say about the conversion here. It says here to change a numeral from one base to base 10, multiply each digit by its respective positional value, then find the sum of the product. And that's exactly what they have done here. We will go through some examples which will give us some practice, and also the worksheets will give you some additional practice, and that should make you comfortable about changing or converting from any base to base 10. And then later on we will also discuss how to do the reverse. That means change a base 10 value to any other base. Okay, so let's see how we can convert a base 4 number to base 10. All right, so the number given to us is 312 base 4. So again, recall the positional values of base 4. So on the extreme right hand side, the right hand digit has a positional value of 4 raised to the power 0, and then the next one will have a positional value of 4 raised to the power 1, then it'll have a value 4 raised to the power 2, and that's how it's going to proceed with the exponents, increasing by 1 as we move from the right to the left. So 312, correct? So let's see. We have 2 for the rightmost digit, so it's going to be 2 multiplied by 1. 4 raised to the power 0 is a 1, so 2 multiplied by 1, and then plus, the next value is 1. The next digit has a value 1, so it's going to be 1 multiplied by 4, plus we have 3. That the positional value of that is 16, so 4 squared, so it's going to be 3 multiplied by 16, correct? So 3 multiplied by 16 is going to be 48 plus 4 plus 2, right? Plus 2. So 48 plus 4 is 52, 52 plus 2 is 54, and that should be the decimal equivalent or the base 10 equivalent of 312 base 4. So let's look at the solutions that they have come up with here. So solution, see, they've done the same thing here. 312 base 4 is equal to 3 times 4 squared, which is a 16, plus 1 times 4, 1 being this middle digit here, 1 times 4 plus 2 times 1, right? So, which amounts to 3 times 16 plus 1 times 4 plus 2 times 1 for 48 plus 4 plus 2, which gives the same answer as what we got here as 54. Now we will look at an interesting fact about bases here, different bases. It says here, notice that 2 base 4 has the same value as 2 base 10 since both are equal to the number 2. And the fact is that that will be true for any base. It'll be true for any base provided that these values, the n, all right, so these values are less than the base b, all right, and the base b is less than or equal to 10, then n sub b equals n sub 10, all right. So if we have a base value of, let's take another base, pick another base here. If we have 5 with base 6, all right, 5 with base 6. This 5, which represents n, is less than the base 6, right? Here, n is 5 and the base is 6. So that condition is met. And the base b is less than or equal to 10. So over here, the base is indeed less than 10. 6 is less than 10. Then we can say that 5 base 6 is going to be the same as whatever 5 base 10 is. All right. And that will be true for any other base as well. If we choose something like 4 base 8, all right, will be equal to 4 base 10. But what are the conditions again that need to be met? First of all, this value here, 4, it should be less than the base value. N should be less than the base value. And the base, which is this, is less than 10. All right. Only then the two sides would be the same. 4 base 8 will be equal to 4 base 10. We're going to look into now how to convert a binary number to a base 10 number. All right. So binary number is a base 2 value, right? And the process of doing that is just the same as we have seen before. All right. We look at each digit one by one, multiply them by its positional values, and then we will sum them up. And the good thing about base 2 numbers is that we are dealing with just two values, 0 and 1, all right, which makes the multiplication process a bit easier than other bases. Okay, so let's go look into the positional values here. If the base is 2, then the positional value starts from 2 to the power 0. Then we have 2 to the power 1, 2 squared, 2 to the power 4, 2 to the power 5, and 2 to the power, oh, we missed a 2 to the power 3. So let me do that again. All right, it should be 2 to the power 3 after 2 squared, 2 cube, 2 to the power 4, and 2 to the power 5. All right. And what we are going to do is we are going to multiply each of these digits here by their corresponding place values and then sum them up. So 2 to the power 0 is a 1, right? So the way we are going to go about is, let's do that here, up here. It's going to be 0. I'm going to start from the right side. So we start with 0 times 1. Right? 2 to the power 0 is 1, plus 2 to the power 1 is 2, so that means 1 times 2, plus 0 times 4, right? 2 squared is a 4, so 0 times 4, plus the next value is also, the next digit is also a 0, so 0 times 2 cube. All right, here we have 2 cube. 2 cube is 8, correct? So times 8, and then 1 times, here, 1 times 2 to the power 4. 2 to the power 4 is 16. So it's going to be plus 1 times 16 plus 1 times, for the extreme leftmost digit, it's going to be 1 times 32. And then we are going to multiply, so 0 plus 2 plus 0, 0 times 4 being a 0, plus another 0 for 0 times 8, plus 16 plus 32, and that would be 2 plus 16, 18, 18 plus 32 is 50. All right, so that should be the answer. I'm going to now pull up the solutions that the PowerPoint is presenting to us, and let's see what they have here. The same thing, all right, so they have multiplied each digit by its corresponding place value. Only thing is they started from the left hand side and then progressed to the right hand side, whereas we started from the right hand side and progressed towards the left hand side. It won't matter as far as the final answer is concerned. It should still give us a value of 50. All right, so doesn't matter whether you start from the left or from the right, you should still get the same answer. All right, and then we have then the next step, 1 times 32 plus 1 times 16 plus 0 times 8 plus 0 times 4 plus 1 times 2 plus 0 times 1. Exactly what we have here. If you read from the left, from the right to the left, they have the same thing here. And then finally, it's 32 plus 16 plus 0 plus 0 plus 2 plus 0 for a value of 50. So they got the same answer as we did. So that's how you're going to do the conversion from a base for a binary base to a base 10 number. But the process is going to be the same whether it's you're converting from base 2 to base 10 or base 4 to base 10 or for any other base which is less than 10, base 10. All right. So how do we go about converting a base 10 value to another base? All right. Now, previously we had done that when we were learning about the Babylonian and the Mayan system, which had bases of 60 and so on. We were using the division method, if you recall, right? We are going to do the same thing here. It says here, divide the base 10 numeral by the highest power of the new base that is less than or equal to the given base 10 numeral and record this quotient. All right, so the quotient tells us how many times a particular number goes into the uh, dividend, right? So that's what we are going to do here. We are going to divide the base 10, the decimal value, to by the highest power, record the quotient, and also record uh, the remainder, if any. All right. And then we will work with the remainder. We will keep dividing the remainder by the next smaller power of the new base and record this quotient. So we are going to work with the remainder until we have no remainder or we cannot divide any further. All right. So we're going to work through an example. Just reading this really uh, won't help until we have actually looked at some example problems and worked and practiced some problems ourselves. So let's go on to the next slide to see if there is an example. So let's work through this example of converting a decimal value, in this case 273, to base 3. All right. Now the first step will be to divide this decimal value by a certain positional value of base 3, which does not go over 273, or rather, let's put it this way, a positional value which is closest to 273 but doesn't go over 273. That means it cannot be greater than 273. So I'm going to first list the different positional values of base 3 so we can pick what positional value we are going to divide 273 by. So the positional values were 3 to the power 0, which had a value of 1, then 3 to the power 1, which has a value of 3, 3 squared was a 9, 3 cubed was a 27, 3 to the power 4 is 81, and then we had 3 to the power 5, which is 243, and the next one is 3 to the power 6, which is 729. All right. Now we clearly see that 243, this positional value in the sixth digit, right? That 6-digit value is 243. That's the value which is closest to 273, but not greater than it. Right? All right. The next positional value is 729, which is greater than 273. So we cannot use that one. We have to divide it by 243. So we are going to do that division. So we are going to go through the process of division in the next slide. But let's see what the solution is provided on the slide here. So it says exactly what we did here. It says the place values in the base 3 system are 3 to the power 6, 5, 4, 3, 2, 1, 2, 1 and 0, or these are the exact values that we gave here: 729, 243, 81, 27, 9, 3 and 1 from the left to the right. So the next step will be the highest power of the base that is less than or equal to 273 is 3 to the power 5 or 243. So we are looking from this list of values of the positional values. We are looking for the value which is closest to 273 without going over, and they find 243 to be the value by which we can start dividing 273. So we will begin by dividing 273 by the positional value, this positional value 243. And we will continue with the process of division in the next slide, right? So here we are performing all the divisions starting with 273. So we pick 243, which is the positional value, one of the positional values of base 3, which was the closest to 273 without going over. So we start with 273, start by dividing 273 with 243, and 243 goes into 273 once. So let's write 243 below 273, subtract, and we end up with 30. So the quotient is a 1, all right? This is the quotient, and 30 is the remainder, correct? It's the remainder. So we write here 1 with remainder 30. That's the result of dividing 273 by 243. The next one, or the next step, would be to divide 30 by the next positional value. And while we are at it, let me just write the different positional values so it's easy for us to realize what we are going to divide the remainder by at each step. All right, so it's 3 to the power 0 is 1, then 3 to the power 1 is a 3, 3 squared is how much is it? 9, 3 cube 27, 3 to the power 4 is 81, 3 to the power 5 was 243, and we don't need the 3 to the power 6 because it's greater than 273. All right, so 1, 3, 9, 27, 81. We already finished our division by 243. I'm going to cross that out. The next place value is 81, correct? So we have to take this remainder, all right, and divide it by 81 and then see what the result is going to be. So 30 divided by 81. 81 goes into 30 how many times? 0 times, right? So 0 as the quotient, so 0 is going to be the quotient. 0 times 81 is 0. So let's write that below the 30, and we are again left with the remainder 30. All right, so quotient is 0, remainder is 30. The way we write it is 30 divided by 81 is 0 with remainder 30. So we have to continue with the process of division. Take this 30 now and divide it by the next positional value. We are done with dividing by 81. The next positional value is 27, correct? So let's do the division. We go to take 30 and divide it by 27. So 27 goes into 31, so I'm going to write a 1 for the quotient, 27 below the 30, subtract it, and we are left with 30 as the remainder. So for 30 divided by 27, we write it as 1 with remainder 3. All right, but we have to keep dividing. 3 now has to be divided by the next positional value. We are done with 27. The next positional value is 9. So we have to divide this 3 by 9. Let's do that. 3 divided by 9 goes into 3 0 times, right? So 9 times 0 is 0, and subtract, and we are left with 3. All right, but so far the result of this division is written as 3 divided by 9 is 0 with remainder 3. All right, let's do the last division here. So we are done with 9. All right, now we have to divide this remainder 3 by this 3 here, by this 3. So let's do that. 3 divided by 3. 3 goes into 3 1, so we write the 1 as the quotient, and then what do we have here? 3. All right, 3, and then 0 for the remainder. So that's going to be the remainder. We write it as 3 divided by 3 equals 1 with remainder 0. All right, but we have to still note this last remainder. We can either note this last remainder, or we can go along with one more division. All right, because we still have this 1 left. All right, this place value left. What you can do is you can take the 0 divided by 1. 1 goes into 0 0 times, so the result is 0. All right, and remainder is now 0. All right, and we can write this as 0 with remainder 0. Or you can either write this, or the way they work it out in this on the slide is they just list this last remainder. They will include it in the as the last digit, or rather when I say last, I should really say the rightmost digit in the of the numeral. All right, so let's see in the next slide how they represent these values 1 0 1 0 1. All the quotient values and the last remainder will form our base 3 numeral equivalent of 273. All right, so after we did the division, we completed all the divisions by all the positional values of base 3, starting from 243 all the way down to 1. All right, we got this value here, 1 0 1 0 1 0. All right, so the positional value of the last 0 was 1, right? 3 to the power 0, let's put it that way. Then the positional value of this one would be 3 to the power 1. Then the next 0 would be 3 squared. Then it would be 3 cubed, 3 to the power 4, and 3 to the power 5 for the extreme left digit. All right, 3 to the power 5. So the way we write it in expanded form, it says we can represent 273 as one group of 243, no groups, 0 groups of 81. 3 to the power 4 was the position, had a place value of 81. then one group of 27, no groups of 9. So this was 9. No groups meaning 0 groups of 9. One group of 3 and 0 and groups of the units of the last rightmost digit. All right, so they have written it now in expanded form. 1 times 243 plus 0 times 81. All right, then this one here times 27 plus 0 times 9. 3 squared is 9. Then 1 times 3 and 0 times 1. Right, this the rightmost digit has a place value 1. Therefore, when we complete this multiplication here, we end up with a value of 101010, and then you have to put the subscript with the base value to indicate what base represents the 273. All right. We will now look at bases greater than 10. All right. So greater than 10 would mean bases of 11, 12, 13, 14, 15, 16 is as high as we go up to. But how do we represent the numerals when we work with bases that are greater than 10? All right. Now, normally we said that we always start from 0. The numerals in any base start from 0 and go up to 1 less than whatever the base is. For example, if we are working with base 12, so let me write that down. If we are working with base 12, then our numerals would start from 0 and then they would be 1, 2, 3, 4, 5, 6, 7, 8, 9, and it should go up to 10 and 11, correct? It should go up to 1 less. The highest value numeral should be 1 less than whatever the base 12 is. However, we do not write the number 10 and 11 when we are working with bases greater than 10. What we do instead is we use letters of the alphabet. So we use the capital A, all right? We use the capital A to represent 10 and the capital B to represent 11. Likewise, if we are working with bases greater than 12, then to represent 12, we will use the next letter in the alphabet after B, which is a C, and then D, E, F. We go all the way up to F if we are working with a base 16, and F would have a value of 15. All right, so that's the convention we use. So let's see what they say here. It says in this textbook, and it's not just in this textbook, it's an accepted convention, and you will find that in most books, all right, in almost every book. So here it says in this textbook, whenever a base larger than 10 is used, we will use the capital letter A to represent 10. So up to 9 we use the different numerals, but once we cross 9 and come to 10, 10 is written as A or represented as A, 11 as B. So we will use the capital letter A to represent 10, the capital letter B to represent 11, capital letter C to represent 12, and so on. All right, so we have to keep those numerals in our heads when we go on to working with bases greater than 10, whether we are converting from one to another or we are performing any computations. Now, up to this point, we had studied bases that were less than 10, less than the decimal base. Now we will look at the bases that are greater than 10, right? So one of them, there are two of them, in fact. One of them is the base 12 system, also called the duodecimal system. So we will begin by looking at base 12, and then we will also look at the base 16 or the hexadecimal system. As you can tell, duodecimal means 2 plus base 10. All right, that makes it 12. Now the symbols in any number system, the numerals will be will start from 0. All right, we'll start from 0 and we'll go up to a value which is 1 less than whatever the base is. All right, so in this case we will have 0 for base 12 is what I'm talking. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then we go up to 10 and 11. All right, however, instead of writing 10 and 11, we use two simple symbols, all right, or rather two letters of the alphabet. So one is A, and that stands for 10, and a B for 11. All right, so we stop at 11, and then the other numbers will be formed by the different digits. But as far as single digit system is concerned, the symbols are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then A and B. A represents 10 and B represents 11 in the duodecimal system, base 12 system. In the base 16 system, also known as the hexadecimal system, we use the symbols. Again, it will start from 0, then 1, 2, 3, 4, 5, 6, 7, 8, 9, but now there'll be A, B, C, D, E, and F. So we have to go up to 15. All right, one less than whatever the base is. So A will be 10, 11, 12, 13, 14, and 15, and we stop there. All right. So let's do a conversion first from base 16 to base 10. All right. Again, the positional values go like this. The extreme right digit in base 16 has a value of 1, a place value of 1, right? 16 raised to the power 0 is 1. The next positional value is 16 raised to the power 1, which is a 16, and then 16 squared is 256, and so on. All right, it goes on like that. So we have 3 digits here, 7DE base 16. We have to convert it to base 10. So the way it's going to work is we take each value here, 7, D, and E, all right, and then we multiply each symbol, all right, each digit rather, by its place value. So we'll start with E times 1, and then the next one is D. So D times 16 plus D times, not D, sorry, 7. I'm sorry here. Let's write 7. This last digit on the left-hand side is a 7. So 7 times the place value for that is 256. All right, and then we are going to first complete the multiplication and then add up. Now, what is E? E stands for what number? We go up to 9, and then let's write that here. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and A, B, C, D, E, correct? So A is 10, B is 11, C 12, D 13, E is 14, right? So it's going to be 14 times 1, and D is going to be 13 times 1, 16. All right, so we are going to end up like this. 7 times 256 plus 13 times 16 plus 14 times 1. All right, so let's see the solution that this particular slide comes up with. But before that, I'm going to erase my writing so that we can read the print. Give me a second here. Right, so okay, so here we go. The solution 7DE base 16, 7 times 16 squared, right? 7 times 16 squared plus D times 16 plus E times 1, correct? So what happens then? In the next step, it's 7 times 256 plus 13 times 16 plus 14 times 1 for a result of 1792 plus 208 plus 14. So the decimal equivalent of 7DE in base 16 is 2014. All right, so this is how you're going to do the conversion from base 16 to base 10. And finally, to convert from a decimal to a base 16 numeral, we have to follow the same process of division that we learned before for bases less than 10. All right, that means we have to take our decimal value and we have to start by dividing this number, the 6713, by a positional value in base 16 that is closest to 6713 without going over. All right, so let's see the solution presented here. It says the highest power of base 16 less than or equal to 6713 is 6 to the power 3, which is 4096. All right, so if I write the positional values here, it would be 16 to the power 0 on the extreme right, which is a 1, 16 squared, 16 to the power 1, 16 to the power 1, all right, which would be 16, then 16 squared, 16 cube, and 16 cube has a value of 4096. All right, so 4096 is what we are going to start the division with. So 6713 divided by 4096, and then if we obtain a quotient greater than 9 but less than 16, we will use the corresponding letter A through F. All right, so let's go through the process of division in the next slide. So here we perform the division. So we start with 6713 divided by 4096, which is the positional value of 16 to the power 3. All right, 16 to the power 3 is 4096, and that's the value closest to 6713 without going over. When we perform the division, it's going to be, the quotient is going to be 1 with remainder 2617. In the next step, we take the remainder 2617 and divide it by the next positional value that comes to the right of 4096, and that's 16 squared. All right, so 16 squared is 256, so we divide 2617 by 256, and the quotient is actually 10, but 10 is symbolized by the letter A in base 16. So we write A for the quotient with remainder 57. Next step, 57 needs to be divided by the next place value to the right of 16 squared. So that's 16 to the power 1 or 16. So 57 divided by 16 is 3 with remainder 9. All right, so the final answer is going to be 1, 8, 3, and 9, the last remainder, or we can divide 9 by the next positional value. So this is how it was, right? This was 4096 was 16 cubed, 256 was 16 squared, 16 was 16 to the 1. If you want, and let me just do this here, it's 16 to the power 1. And we can do this, we can take this remainder 9 divided by 1, all right? And then it can be 9 with remainder 0, and then we can put these four quotients, put them together to come up with the base 16 equivalent of 6713. All right, so the final answer is going to be 1A39. So you see over here all the quotient values, 1A39. Now if you don't want to do the last division, you can just use like they have done here. All right, they have just used the last remainder, so the quotients of all these divisions, and then include the last remainder in the uh, as part of the base 16 numeral.